Hello, my name is Ming, and I am here to present our work on autonomous vehicle-cyclist interaction. I'm going to start by talking about vehicle-cyclist interaction in the present day. Currently, vehicles and cyclists can communicate on the road in various ways, including vehicle motion and signals such as horns and hand gestures. Eye contact between drivers and cyclists can also be important in order to ensure that the driver is aware of the cyclist. Shoulder checking is an important action for cyclists to check their blind spots before making a move and to allow them to see any vehicle or driver cues that nearby vehicles may be providing. However, in the future, as autonomous vehicles are introduced to the road, cyclists will not be able to rely on driver cues anymore. Autonomous vehicles will have complex suites of sensors to detect cyclists, other road users, and objects. We think it will be important for those vehicles to provide explicit interfaces to help communicate feedback based on that sensor data. To that end, the question we seek to address is, how can autonomous vehicle-cyclist interfaces communicate with cyclists on the road? Interfaces can provide an opportunity not only to fill the communication gap left by drivers, but to provide additional useful information beyond what is available in a typical vehicle-cyclist interaction today. While there has been previous work looking into the use of interfaces for autonomous vehicle-pedestrian and autonomous vehicle-cyclist communication during street crossing scenarios, we found that those works did not distinguish between AV-pedestrian and AV-cyclist interaction. The use of interfaces in scenarios that were unique to cyclists, such as road cycling, were mostly unexplored. We also found previous work that looked into how warning and navigational cues could be communicated to cyclists, and so we wanted to explore how autonomous vehicles could leverage different types of cues and interface locations to communicate specifically with cyclists. Because there are a variety of vehicle-cyclist interaction scenarios, we decided to narrow it down to the cyclist merging scenario for our initial exploration. The main reason for this was that this interaction accounted for the majority of vehicle-cyclist accidents, and it provides a scenario where the cyclist only has occasional view of vehicles behind them through shoulder checking, which is a problem that is relatively unique to cyclists when compared to other vulnerable road users. To help conceptualize some interfaces for this scenario, we conducted a preliminary interface design study with 10 participants to understand what modes of communication people expect from AVs when cycling, and how interfaces could address those expectations. We provided participants with a sheet depicting a cyclist on a road shoulder in front of an autonomous vehicle and asked them to brainstorm different ways the vehicle could communicate to the cyclist, whether or not it was safe to merge. Participants could then draw or place labels on the sheet to outline their ideas. To help them get started, we provided some basic labels for several modalities, such as display, speaker, and haptic feedback. But participants could freely create and add any additional labels that they wanted to. In the example on this slide, you can see that the participant created an interface that uses laser projections to communicate with the cyclist by projecting beside them on the road. From our design study, we obtained 32 designs and made some interesting findings that we used to inform our later designs for our user studies, which is detailed more in depth in the paper. From these interfaces, we identified the most common components and cues and came up with 6 interfaces across 3 modalities. The 3 main modalities we touched on are visual cues, auditory cues, and haptic cues, which in this case involve vibrating the bicycle handlebars. To assess our interfaces, we decided to create an immersive virtual reality cyclist simulator. Virtual reality was chosen because it is safer and much less cost prohibitive than physical prototyping. The simulation was created in Unity, and the headset we used was an Oculus Quest, which has the significant advantage of being wireless, which allows for better immersion and results in fewer issues when dealing with a bicycle. For the bicycle, we used a city bike held in place by an indoor bike trainer. On the rear hub of the bicycle, we mounted a Garmin speed sensor that can monitor and transmit wheel rotations to the Quest headset. To capture bicycle turns, a Quest controller was mounted on the handlebar. The environment of the simulation is a one-way, 2-lane city road with shoulders for the cyclist to ride on. The road is populated by autonomous, driverless vehicles moving at speeds of 50 km per hour, with interfaces that can be toggled on or off. We implemented our 6 interfaces from the design study into simulation. The first interface, as you can see in this slide, is a laser projection that appears on the road beside the cyclist with a binary safe or unsafe merging cue. The safe cue is a green bicycle, while the unsafe cue is a red hand. Then we have a window display that is green when it is safe to merge, and red when it is unsafe. It is important to note that for this interface, the cyclist has a shoulder check to view it, unlike the other interfaces which usually don't require shoulder checks to see or hear. Next, we have a bicycle heads-up display that shows the distance of nearby vehicles behind the cyclist. With regards to auditory interfaces, we have a verbal audio cue, which simply plays a voice clip that says merge when it is safe to merge, and don't merge when it is not. For our nonverbal cue, the safe cue is a chirp similar to the ones that play at crosswalks, and the unsafe cue is a buzzer. For our haptic interface, we vibrated a controller that was placed on the handlebar, which will indicate to the cyclist that it is safe to merge. Using our simulator, we conducted a user study with 18 participants. We first gave participants a pre-study questionnaire asking about their cycling experience and demographics. During the study, participants were tasked with riding down a road shoulder, and they had to merge into traffic in order to avoid occasional obstacles such as parked scooters that appeared in front of them, and they had to merge back after passing the obstacle. We assessed how participants responded to the cues provided by each interface when performing this task, as well as the baseline condition with none of the interfaces, which required the cyclist to interpret vehicle motion in order to make decisions. For each interface, we had free distance conditions corresponding to the spawn distance of vehicles that appeared behind the participant before they had to merge. As you can see in the images on this slide, when the participant reached a certain distance from an obstacle, autonomous vehicles spawned either 24, 48, or 72 meters behind them, and each distance occurred once for each interface. This was to create varied scenarios where the participants may have had to react differently depending on how far or close vehicles were behind them. With 6 interfaces plus the baseline, this resulted in 21 trials in total for each participant. During each trial, we kept track of whether the participant shoulder checked and whether or not they stopped and waited for vehicles behind them to pass before merging into traffic. That way, we could gauge how participants relied on and interpreted each interface. After each trial, we also verbally asked participants to rate on a scale of 1 to 5 their level of confidence in their merging decision and how helpful they found the interface to be for the decision. Participants also completed a post-study questionnaire to rank the interfaces and provide their thoughts about the overall experience and individual interfaces. From our study, we found that all interfaces except for the windshield display yielded statistically significant improvements in the participants' confidence when merging when compared to the baseline with no interface. In addition to the confidence score effect, participants also considered interfaces to be more useful than interpreting vehicle motion, like they had to do when dealing with the baseline scenario. We found that participants overall preferred visual interfaces that were situated off the vehicle and in front of the bicycle the most, and that they felt more confident when interacting with those interfaces. We think this is because the cues could be easily viewed without shoulder checking, and the visual interfaces were more readily available than the audio and haptic interfaces, since it could be viewed at any time, unlike the audio and haptic interfaces, which usually played at specific moments. With regards to interface complexity and location, visibility and glanceability are important considerations, which is what we found in our study since participants valued having interfaces that were easy to see and interpret. This is particularly relevant for cyclists due to the fact that in many situations, they only have brief intermittent views of nearby vehicles, and as a result, we believe our approach of simple cues that communicate basic positioning information or binary safe or unsafe merging conditions is worth further exploration. However, it is important to consider some of the implementation challenges that our interface prototypes might face in the real world, such as the fact that some of the cues will require wireless communication between vehicles and bicycles, and that the visibility and audibility of interfaces might face challenges under certain conditions, such as harsh sunlight in the case of visibility. One way to offset these risks would be to provide redundant cues, but the overall implementation challenges require further exploration. Based on our findings, we also have key takeaways on the implication of AV-cyclist interfaces for cycling culture and safety in the future. Prior research has shown that safety concerns in traffic are a major deterrent to cycling for a large portion of the population. While collision rates for cyclists on roads are low overall, it is the perception of danger that deters many from cycling. For example, in our pre-study questionnaire, we found that 16 out of 18 of our participants said they would cycle more if they felt safer cycling on traffic. In our study, we found that the introduction of interfaces allowed for improved certainty and perception of safety in vehicle-cyclist interactions, as reflected by the overall increase in confidence that participants expressed when interacting with interfaces. Therefore, we believe that AV-cyclist interfaces can help reduce risk concerns and lower the barrier to cycling, which would promote cycling as a safer mode of transportation. However, with some of the potential benefits of AV-cyclist interfaces highlighted previously, it is also important to outline some of the risks that such interfaces may pose. One important aspect of this is trust in the interfaces. Only 4 out of 18 participants said they trusted the simulation vehicles in the emerging scenario without an interface, but this number jumped to 17 out of 18 once an interface was present. While interfaces helped the autonomous vehicles gain the trust of participants, their introduction also caused a decrease in shoulder checking. Participants shoulder checked only around 10% of the time when they were receiving cues that did not require shoulder checking, which would be for all interfaces except for the car window screen and baseline condition. This corresponds to only 29 out of 270 total trials from interfaces that did not explicitly require shoulder checking. We think this is indicative of the participants developing a blind trust in the interfaces, since by not shoulder checking, they decided not to confirm the interface messages with their own eyes. Furthermore, we found that 12 out of 18 participants also believed that the interfaces reduced the responsibility of cyclists in an emerging scenario. This can be dangerous in scenarios such as malfunctions or sensor misreadings. It is also important to consider mixed traffic scenarios where not all vehicles will necessarily be autonomous or have interfaces, further diminishing the ability of cyclists to rely on specific cues. So it is important that future AV-cyclist interfaces are carefully designed and tested to dissuade cyclists from taking unnecessary risks. For future work, we want to explore a larger subset of potential autonomous vehicle-cyclist interactions, since there may be scenarios such as intersections that may introduce additional factors to consider in interface design. Scale is also another important direction, as real-world interactions may often involve multiple vehicles interacting with multiple cyclists at once. Similarly, it would also be important to explore heterogeneous traffic interactions, since in reality, homogeneous traffic is a long time away, and autonomous vehicles will instead be gradually introduced to roads alongside vehicles with human drivers. Multimodal interfaces could also be looked at, since we mainly touched on multimodal cues. In terms of key takeaways of this presentation, we would like to highlight first that autonomous vehicle-cyclist interfaces can play a crucial role in promoting cycling in the future by alleviating safety concerns for cycling on the road once autonomous vehicle traffic becomes commonplace. However, secondly, it is important to consider how interfaces can influence a cyclist's risk perception by potentially causing them to become over-reliant on interfaces. Thank you for listening to our talk. Our contact information is included on this slide.